Cool. Thanks everybody for coming. And I am excited to introduce Alessandra, who's going to tell us about Cohen-Macaulay property of the fiber cone of modules. Alessandra.
Thank you. Thank you very much for letting me speak at CHAMP. This is a really nice initiative. So today I'm going to be talking about the Cohen-Macaulay property of the fiber cone of modules. But of course, I'm going to start a little bit with some introductions. First of all, I'm going to tell you what the fiber cone of a module is. And then the beginning of the talk is going to be sort of like a review of what happens for fiber cone of ideals. So let me get started. The setting for the whole talk is going to be, we're going to be talking about Noetherian local rings in finite modules with a rank. If you don't remember what this condition means, it means that when you pick your module and you tensor with total ring of quotients, and that's going to be a free module of rank E. And so this is not a restrictive assumption because if you're over a domain, every finally generated module is a ring. Otherwise, it's enough for your modules to have finite projective dimensions. So it's really a wide enough class of ideals. So in this setting, let's say that we have a presentation of this form for our module. Then, given this presentation matrix, we can define the symmetric algebra S of E as the quotient ring of R. We adjoin as many variables as the number of generators, and we go modulo as many linear forms as the domain here, the cardinality of the domain. So this is the symmetric algebra. And the linear forms are so that the the vector generated by linear forms is the dot product of the vector of the t variables times phi. Okay. And from the symmetric algebra, what we do is that we go modulo the R torsion submodule. And that's where the Riverside algebra comes in. And then the last thing we do is we go modulo M RE, or if you want, we are tensoring with the residue field over R. And that's going to be what we call the fiber cone. So this was the Riverside algebra. Okay. So before I lose everybody here, let me just give some very easy examples. So of course, the first very trivial example is that you pick E to be a free module. Then say RTN, then at that point, the symmetric algebra of E is the same as the Riverside algebra of E and is just the polynomial ring. So super easy case. And then the fiber cone would be the same polynomial ring, but now with coefficients in the field. Okay, so that's the easiest example you can think of. Then the second easiest example is if you pick E to be a torsion-free module of rank 1. Well, torsion-free modules of rank 1 are isomorphic to an ideal of positive grade. And in this case, the Riverside algebra of I, so still you can do all of this construction as a quotient of the symmetric algebra modulo distortion, but now this becomes an object that is possibly more familiar, is the subalgebra R of IT defined as sum I bigger or equal than 0, I to the I, t to the I of the polynomial ring R of T. Okay, and you might have encountered this object, for example, when studying properties of filtrations of ideals in dimension theory and things like that for the art and Riverside lemma and these kind of things in your basic commutative algebra classes. And of course, in general, here we have that the algebra of I basically is packing information about the property of I. So from an algebraic point of view, this algebra comes out a lot when you are interested in studying the powers of I. And even with the asymptotic behavior, even in that case, f of I, again, is going to be R of I tensor K. This algebra here comes in play a lot when you're interested in asymptotic behaviors of the powers of I. So what's the motivation of studying these algebras? Well, most of the motivations come from geometry. And the most famous example is the blow-up constructions. So you have a singular variety at a singular point. So I is the ideal corresponding to the variety. And what happens is that the algebra is going to be the homogeneous coordinate ring of the blow-up. Then you have the associated graded ring. That probably I should actually write here just in case. I to the I over I to the I plus 1. This one is isomorphic to the sum I to the I m over I to the I. Okay, so we have these three rings. And the associated graded ring corresponds to the exceptional set of the blow-up. Which is also known as the tangent cone. And the special fiber ring, the fiber cone of special fiber ring is corresponding to the special fiber of the blow-up at the unique close point. And this procedure of blow-up was introduced in order to possibly resolve singularities. You have a singularity, you blow it up, and your hope is that the new variety you obtain is not singular anymore. Sometimes to do this, you actually need to repeat the blow-up procedure more than once, and that's when you obtain some geometric objects whose corresponding algebraic counterparts are the algebra of a direct sum of ideals and the fiber cone. So a direct sum of ideals, this would be the blow-up at, if you want this as sequence of successive blow-ups. Low ups along V of I1 and then V of IS. And I think I want this to be disjoint ideals. And again, this is going to be the special fiber of the same thing. So blow-up constructions are definitely the most important geometric classes of examples where Riverside algebras and fiber cones come in play. But also another source is some objects that are related with projective varieties. So whenever you have subvarieties of a projective space, you can always construct rational map by picking element homogeneous polynomial of all the same degree. In this case, the graph of phi is going to be the biprojective spectrum of the Riverside algebra of I, where I is the ideal generated by all of my F's. And the image is going to be the projective spectrum of the fiber cone. And the other constructions that we can do in this case that don't come from blow up, don't come as images of rational map, are the second variety and the tangent variety. So the second variety is going to be the projective spectrum of the fiber cone of D, where D is what is called the diagonal ideal, which is the kernel of this map. The map that goes from R tensor over K R into R, where R is the coordinate ring of your variety. And the tangent of X is the projective spectrum of the fiber cone of the module of differentials of R, which is an object that is really interesting when you want to study the singularities of R, and Ben Bridge talked about it last time. Finally, another example, again, this is a rational map, but in this case, it's going to correspond to Riesz algebras of modules that are not ideals, and it's the Gauss map that associate to every point the tangent space at that point. So in this case, we have that the graph of N is the biprojective spectrum. Sorry, this is affine, so this is just the projective spectrum of what? Of the deep exterior power of the modules of differentials. Sorry, I forgot an R here. So that's the Riesz algebra of this thing. And then for the image, we have the same thing. But with the fiber cone. Okay. So hopefully this list of examples give you an idea why geometers are interested in Riesz algebras. Why do you care about Riesz algebra and fiber cones of modules that are not ideals from an algebraic perspective? This has to deal with applications to integral dependence and multiplicity theory. I'm not going to get into the details of that, but like really integral dependence and multiplicity are the algebraic counterpart of these objects here. When you study birational geometry, that's algebraically what you're doing. Okay, so it's sort of like a geometric overview. And now I want to talk about the Cohen-Macaulay property. And the motivation comes really, first of all, from the blow-up constructions. The idea is if you start off with a Cohen-Macaulay ring, so if you have a Cohen-Macaulay variety, what you would like to do is you want to know whether or not after blowing up, you're still a Cohen-Macaulay kind of singularity. And this is not always true. Sometimes it is the case, sometimes it is not. But what is interesting is that one can relate the Cohen-Macaulay property of all of the three algebras related to the blow-up construction. So the story goes like this. In 1982, Unique showed this direction. And actually, sorry, I'm going to zoom this out a bit, because I want to emphasize one thing, that really here we're seeing the associated graded ring as a factor ring of the Riesz algebra. That's really the key part of this proof. So with this, using this isomorphism, he shows that when the Riesz algebra is Cohen-Macaulay, the associated graded ring is Cohen-Macaulay. The backward is not true in general, like he gives a counterexample in that paper. However, the backward is true if there are some additional numerical conditions that are satisfied. And let me list some people here. So Trunghi-Keda is the most famous. And that's a condition on the A invariant of the associated graded ring. So it requires you to study the canonical module of the associated graded ring or the local cohomology of the associated graded ring. Then there is Johnston-Katz, and that's a condition on the reduction number, which is a numerical invariant related to the powers of your ideal. And let me stop here. There are also other things, but so this is still in the late 80s, beginning of 90s. And then there is this weird guy down here whose Cohen-Macaulay property is kind of wild in the sense that there are counterexamples showing that it is unrelated to that of the Riesz algebra and the fiber cone in both directions, actually. And in this direction, this way, it's pretty easy to construct examples. Like you can pick a perfect ideal of I2 and construct an example that satisfies these two Cohen-Macaulay, but this not Cohen-Macaulay. And for this direction here, this is a counterexample of Heinzer. Sorry, let me list in alphabetical order. Danna, Anna Guerrieri, and Heinzer. And this is still 1999, I believe. So they construct an example of an ideal whose fiber cone is Cohen-Macaulay, but the Riesz algebra and the associated graded ring are not. And in general, determining when the associated graded ring and the fiber cone are Cohen-Macaulay are really two different stories. Like the techniques used in the two cases are very different. And I want to emphasize a bit this part of the story. This is really telling you that in order to understand when the Riesz algebra of an ideal is Cohen-Macaulay, you can really transfer the problem to study the associated graded ring. And they gave rise to an incredible amount of literature. In the 80s and 90s, this was the hot topic in commutative algebra. Like half of the people working in commutative algebra were working on this. And what happens with modules? So we have a big issue with modules. We can still define what is the power of a module. This is really defined to be the ith graded component of the Riesz algebra. And this is really to mimic the definition in the case of ideals. But the problem is that I to the I plus 1 is not containing I to the I anymore. Just think, for example, when I is equal 0, a module is not contained into a ring. And that creates a huge issue because there is nothing that looks like this. Really, you cannot write e to the I over e to the I plus 1. So what happens here is that basically the usual strategy that you would do, you first study the Cohen-Macaulayness of the associated ring, and then you work on this numerical condition, doesn't work anymore. And you need a different strategy. And this makes the literature on this Cohen-Macaulay property of Riesz algebras of modules much shorter. Let me just say very briefly that the multigraded case, the multi-Riesz ring, so I'm talking about Riesz algebras of the direct sum of ideals. This is kind of very well studied, but it's sort of like special because the fact that this is a direct sum is giving extra structure that you wouldn't usually have for modules. And very little for modules that are not a direct sum of ideals. So something like with small projective dimensions and very little for fiber cones. And to the extent for fiber cones, what we know is something about the fiber cone of direct sum of powers of the maximal ideal, something like that, or something for fiber cone of E, where E is either of finite length or of finite co-length. And these papers are recent. So these would be Miranda Neto and it was published this year. For finite length is Rishan Jayantan, 2018. And in general, even in the case of ideals, the literature about the fiber cone is much later than the literature about the associated ring. It feels like even in the case of fiber cone of ideals, there is still a lot to be understood. Okay, so how do we deal with this in the case of modules? The general technique that people uses in this case is the most general technique, goes back to 2003 from Simis, Ulrich, and Vasconcelos. And basically, this is sort of like a recipe to substitute for Unique's theorem. With Unique's theorem, the idea was, if you want to understand the Cohen-Macaulay property of Riesz algebras, you reduce to the case of the associated graded ring. In this case, we are exploiting the fact, remember I said it at the beginning, that modules, torsion-free modules of rank 1 are isomorphic to ideals. So the story goes, you want to kind of do induction on the rank. So you start with modules, finite generated modules with ranks, and then you do a generic extension. So you construct a set of variables, Cij, where I is the index that keeps track of the number of generators, and J keeps track of the rank. So you go on up to 1 minus the rank. Then you construct the polynomial ring adjoining in all of these variables, and you call it R prime. Then you construct the ring R double prime, which is, after you got here, you localize the image of the maximal ideal. This is local again. And this is a faithfully flat extension of R, which is crucial in the theory. And then you define your module E double prime to be E tensor or R double prime. Then you construct elements Xj to be a generic combination of the generators of your module. You pick your elements A sub I inside the submodule. It's very common to pick this as the generators of your module, but it's not required. Okay, so this is some I1 to N. And then you construct the module F double prime to be the sum J1 to E of these elements Xj. Okay, now this sounds kind of complicated, but what happens is that if E is torsion free, maybe I should write this as a theorem though. And again, this is the main theorem, one of the main theorems of Simis, Ulrich, and Vasconcelos. If E is torsion free and locally free at primes P, so that the depth of RP is at most 1, then E double prime mod F double prime is isomorphic to an ideal I in R double prime. And this is called, let me write it in blue, a generic Bourbaki ideal of E with respect to U, just because we picked this element as a by in U. And the main theorem, the magic that happens here, is this result here that I'm going to drag up here. If you do this, picking U to be a reduction of E. So a reduction is a special submodule of E that, let's say, it helps you keeping track of the powers of the module. Okay. And in this case, the Riesz algebra of the module is Cohen-Macaulay if and only if the Riesz algebra of the ideal is Cohen-Macaulay. And whenever this happens, the Riesz algebra of I is going to be a quotient of the Riesz algebra of the module E after you pass to the generic extension, modulo this F here. And these guys, x1, xe minus 1, so these were the module generators of F double prime, form a regular sequence. So really what's happening here is that the Cohen-Macaulay property passes back and forth because you manage to rewrite your R of I as a quotient ring of R of E double prime, modulo regular sequence. That's really the trick here. Okay, and let me also add some terminology. This is telling you that R of I is a deformation of R of E double prime. Okay, so that's really the key there. And this was like working on the Cohen-Macaulay property of Riesz algebra was the main goal of my thesis. Like basically in the paper of Simis, Urris, and Vasconcelos, they have this result, but then the real struggle is to find sufficient conditions for the Riesz algebra of a module to be Cohen-Macaulay. This recipe is telling you, you construct a generic Bourbaki ideal, then you figure out what assumptions you need on your ideal I to be Cohen-Macaulay and for the Riesz algebra to be Cohen-Macaulay, and you bring the Cohen-Macaulayness back. The problem is that it's hard to figure out what assumptions you need on the module so that the ideal I does all of that. And so when I was...
Sorry. So just to be clear, even the number of like generic elements you pick to build this U doesn't matter?
Oh, good question. Actually, it's something you have to prove. And that's the main reason why we go to the R double prime, not just to R prime. What happens is that this may not exist because this is a sufficient condition, but a priori may not exist. But once you have this construction in place, you can show that if you started off with two different generating sets for U, as long as you allow yourself to possibly add more variables in the bigger ring. So like when you have all of the variables you need for this set of generators and all of the variables you will need for your alternate set of generators, these two ideals would extend to the same ideal in an even larger ring.
And but so in this theorem 1, it also doesn't matter how many generators your U has. That's also... It
doesn't. I mean, what I'm saying here is that whatever generating set of U you pick, you can do the proof. But thanks, that was actually a very good question, and it's really part of the need of this. Like, I mean, this is called generic Bourbaki ideal. The generic part comes from extending the ring. Bourbaki ideal, really, here what you're having is this, that you have an exact sequence. Okay, and what happens here is that this guy is free, and this is an ideal. So except for the extension thing, like whenever you have a sequence like this, where you have a free module, an ideal, and your module in between, this is called a Bourbaki sequence and was introduced back in the 60s. Okay, so back to what I was saying, finding sufficient conditions for the Cohen-Macaulayness of the Riesz algebra module was my main work for my thesis. And I was giving a talk about it like a year and a half ago in New Mexico State. And Jonathan was in the audience and he asked me, well, what about the fiber cone? And that's how this project started. What about the fiber cone? And most specifically, the question is, here, the key property is to make sure that this deformation property happens. The question is, okay, can we find conditions so that we have a deformation also at fiber cone level? And if that's the case, can we use these Bourbaki ideals to study the Cohen-Macaulay property of fiber cones? And I really want to underline that there is no general technique to study the Cohen-Macaulay property of fiber cones that works for every module or kind of. Okay, like the examples that are known are about modules with finite length. So what happens here? Let me drag the beginning of my theorem, which I was a little lazy to write. So I'm picking the usual assumption that you would have in a Bourbaki ideal contest: Noetherian local ring, finite modules of finite rank. You pick U to be a reduction, and you pick a generic Bourbaki ideal of A with respect to this reduction. So a priori, this may not exist, but what I'm saying is, like, assume that this module has a generic Bourbaki ideal, then what do I need to have this deformation happen? So here are my examples. I assume that one of these conditions holds, so you don't need all of them. The first is the depth of f of E is at least the rank. The second, and this is going to look mysterious, but I'm going to get back to it I'm going to explain it in a second. The Riesz algebra of the Bourbaki ideal is S2. And the alternative condition I have here is, it looks technical, but then I'm going to tell you where it comes from, and hopefully you will accept the technicality. Okay, I want that the depth of the Riesz algebra of the ideal localized at Q is at least 2 for any Q in spec of R double prime, so that IQ is not of linear type. So linear type means, let me write it here, means that symmetric algebra of I is the same as the Riesz algebra. So these are very special classes of ideals, kind of rare. For example, the complete intersection ideal is going to be linear type, but not much farther from that. And then if one of these conditions happens, you have this deformation property that I was shooting at. Okay, so let me tell you a bit where this condition come from. And to do so, I need to go back, pardon me, to the previous slide. How do we prove that these Cohen-Macaulay conditions goes back and forth? Well, in this direction, when the Riesz algebra is Cohen-Macaulay, you happen to have that the grade of the Riesz algebra, the grade of the positive part of the Riesz algebra is at least a rank. And that's the condition you need to prove this implication. What happens here is that if you replace that condition on the grade of the unique maximal ideal of the Riesz algebra with the depth of the fiber cone, at least the rank, this will allow a deformation in this case, and we'll see later that that's gonna let you prove that if f of E is Cohen-Macaulay, then f of I is Cohen-Macaulay. These two conditions here instead are two conditions that allow this deformation property to happen, especially when you know that R of I is Cohen-Macaulay. So those are kind of underlining the proof of this direction. And to be more precise, this is the condition that appears in the proof of Simis-Ulrich and Vasconcelos. This other one comes from another result that I have, and it's about the defining equations of Riesz algebras. Basically, when you have a deformation property like this, what happens is that sometimes you are able to study the defining ideal of the Riesz algebra of a module, starting off the defining ideal of the Riesz algebra of its generic Bourbaki ideal. And this condition here, I needed to figure it out because in my case, the Riesz algebra of the ideal I needed to work with was not Cohen-Macaulay, so I couldn't use their theorem to have this deformation property. So this really came from studying the Riesz algebra. So basically what's happening here is that one of these two assumptions, 2 and 3, will guarantee that the Riesz algebra is a deformation, and in turn that will make the fiber cone to be a deformation. And this gives us as a corollary a Cohen-Macaulay-ness result. Actually, you know what? I'm just gonna be lazy again and copy the first 2 rows of my theorem because that's really the same beginning. Okay, but now this is called theorem 3. Okay. So then the first part is telling you that if the fiber cone of the module is Cohen-Macaulay, then the fiber cone of the generic Bourbaki ideal is going to be Cohen-Macaulay. And this uses part 1. And then if either 2 or 3 from theorem 2 are satisfied, then Fi Cohen-Macaulay implies F of E Cohen-Macaulay. So that's the main result that is telling you how you can reduce the problem of studying the Cohen-Macaulay-ness of fiber cone of modules to the case of ideals using generic Bourbaki ideals. What is making it trickier than in the Riesz algebra case is that you need these conditions for this direction. And in general, is more of like, I was not able to prove that you can obtain this deformation property going in this direction unless I was making assumptions on the Riesz algebra. I haven't figured out a way to do this without going through the Riesz algebra, but I'm really hopeful that this works. I really hope that maybe in some classes of modules, this happens without knowing anything about the Riesz algebra. And it will be important to know it without prior information of the Riesz algebras, because sometimes in order to understand Riesz algebras, at least in the case of ideals, in order to understand Riesz algebra, sometimes you go first and look at the fiber cone. So it will be important to have that kind of situations that you are able to understand the fiber cone of a module without looking at the Riesz algebras. And of course, this is just telling you you can reduce the problem to the case of ideals. Then of course you want to know, well, can you give me at least one sufficient conditions for the fiber cone of a module to be Cohen-Macaulay? And now that's the scary slide of my talk. I hope it's not going to be too overwhelming, but that's how long the theorem is. I'm going to go through it quite shortly though. Okay, so first thing, there is a small reduction on the ring here. It's a small extra assumptions. We need the ring to be Gorenstein. And we also want an infinite residue field. If you work with Riesz algebras or with minimal reductions, this is a very common assumption. So it's basically something that we all come back to at some point because we need to use network normalization as an underlying proof of our main theorem. Then the orientable part here, it's kind of an extra addition. So the definition is a condition about the eth exterior power of your module, where E is the rank. But really what it all does is that it makes the height of the generic Bourbaki ideal that you can construct at least 2. So it's a condition on the height of the generic Bourbaki ideal. Then we have these 4 conditions in blue that will guarantee that the result was Cohen-Macaulay. And these extra 2 conditions in red that would guarantee that the fiber cone is Cohen-Macaulay. So really, this is a result that tells you a class of modules for which both the result and the fiber cone are Cohen-Macaulay. And really, I'm just forcing this deformation property this way. I'm assuming that the result is Cohen-Macaulay, so this is the condition that is going to be satisfied. So where these conditions come from? So the blue conditions, and just for, oh, first of all, sorry, I'm needing to expand on something. The GL condition here, if you've never seen it before, this is just telling you that the minimal number of generators of your modules is the most, the analytic spread, sorry, is the most L minus E plus 1. Sorry, is the most the dimension, here we go, of our P for all primes, so that the dimension of our P is the most L minus E, and that's where I stop. So 1 less than this. And this is a technical condition that is needed in the proof. And what I want to say about this is that you can rephrase this condition on the minimal number of generators in terms of the height of ideals of minors of a presentation matrix. So this is really some condition that Macaulay 2 can compute for you. And if you were in the workshop at Notre Dame last summer, well, summer 2019, I guess, we did problems on Macaulay 2 with this. So this is really not a problem. Then the assumption on the reduction number is still a very common assumption. Let me say that assumptions 1, in the case of rank 1, if you have assumptions 1, 2, and 3 together, then this is a famous result of Johnson and Ulrich. And separately, independently, Goto, Nakamura, and Nishida from 1996. That is basically telling you that when your modules have bounded reduction number and they have a strong assumption, sorry, you have a lower bound for the depth of each power, so the bound depends on the exponent, then the result was Cohen-Macaulay. What happens is that in the case of modules of rank at least 2, if the Bourbaki ideal happens to have height at least height equal to 2, which is, by the way, the most common case happening, so this condition is really relevant, you need this extra condition here. That is kind of manageable because it's a vanishing of X. And this is technical conditions that allow to make the deformation property in terms of the associated of the generic Bourbaki ideal. So all of these conditions guarantee that the result is Cohen-Macaulay. And the remaining 2 conditions are conditions on the number of generators of your module in relation also with the generating relations of the fiber cone. Then in this case, also the fiber cone is Cohen-Macaulay. And for E equal 1, this is a result by Corso, Ghezzi, Pollini, and Ulrich from 2003, I believe. Maybe some 2000, I don't remember the year. Okay. And the whole underlying theory in the ideal case for both of these theorems is that the ideals they consider have good residual intersection properties. So it's something that is related with linkage. And here what I'm doing is really using the generic Bourbaki ideals to bring that result to modules. But it's kind of like tricky because these properties, when you define them for ideals, they make a lot of sense in terms of residual intersections, but you don't have a well understood notion of residual intersections of a module. So that was kind of like a tricky way. And that's why it gets like these very technical assumptions. It's like, really, we have to play around the fact that we don't have residual intersections for modules. How much time do I still have?
3 minutes.
Okay, maybe I can say a little bit of where to go from here. So where to go from here is actually also where I started from, because so this theorem that I'm showing here is a theorem that was in Jonathan's thesis. And he was talking about this when I was at the time of like halfway through my PhD, in the moment of trying to choose my thesis topic. And I'm like, that's my thesis topic. I want to study depth of blow-up algebras. And so this is a nice result that relates for ideals with, let me just say this is like blind box. This means good residual intersection properties. This is a nice result that relates the Cohen-Macaulayness of the associated Gödel ring, the fiber cone, and the Riese algebra. And there is a depth condition here involved that is similar to the ones you've just seen in the theorem before. And the essential hypothesis here is a condition of on the minimal reductions of the ideal I, so this condition here. And so my instinct was, well, I want to have this theorem for modules. Once I got my main Cohen-Macaulayness result for fiber cones of modules, in my thesis, I wrote down this result here. So assume that the first 4 conditions from the previous theorem, so if you remember, there were the blue conditions, the one that guaranteed that the Riese algebra of the module is Cohen-Macaulay. Then our previous results tell us you will have the deformation property you need at fiber cone level. This condition on the minimal reductions replaces this condition here. And what I can prove is that if the fiber cone of E is the fiber cone of E is Cohen-Macaulay and the A invariant of the reduction of the fiber cone satisfies a bound that is basically the analogous of this. So really what I have is this implication. If I'm putting myself in the conditions when the Riese algebra is Cohen-Macaulay, these conditions here, and I'm implying this. Now the problem is that there is no way I can get this other part, which I really would like to have. In this case, notice that this bound here on the reduction number is actually something that I'm assuming. This condition here is basically a rephrasing of that condition on the reduction number. But I cannot get this part. And what's missing is that really this condition here, this is a condition on the core I, which you might be familiar with if you work with integral dependence of ideals, but this is the intersection of all minimal reductions. And so what's missing here is that we don't understand the core of a module. And this is an ongoing work with Luisa Foley and Zhu Yun Hong. We just started, so I'm not going to say anything about it. But I think that that's where I'm going to stop.
Wonderful. Let's thank Alessandra. And are there any questions?
So you have all these blue conditions that that imply that your results of your model is Cohen-Macaulay. Do you have any thoughts over whether any of these is necessary? Do you have any examples of of Cohen-Macaulay results of models that don't satisfy any of these, or?
So that's a good question. So first of all, let me tell you that the first thing I don't like of this theorem is that this theorem, the assumptions are like the minimal I need to make the proof work, but actually they are not the minimal I would want to have, in the sense that when you pick the case E equal 1, this depth condition here, in the case of ideals, I would only have this lower depth condition. Like this is a depth condition that is less strong than the bigger one. So I would have this bound for all the possible J's. And the reason why I need to split this part is that this depth condition makes what make you be able to understand the powers of I, so that you can figure out the Cohen-Macaulayness of the algebras, combined with a good residual intersection property that is called Artin-Nagata. And here I don't have the Artin-Nagata condition because I cannot define it. So this is kind of like the stronger depth is a way to get in around. So that's already the first part where this theorem gets tricky. In the case of ideals, I'm having a theorem that is stronger than this. And why would I want to have a statement where the depth condition is not this strong, but is actually the perfect analog of what you would have in the case of ideals? There is a result of Getzi, where actually she gives formula to calculate the depth of the associated graded ring and of the result in the case where the result was not Cohen-Macaulay, that is playing around with these depth bounds. But in my case, I cannot recover that result. So that's the first part where this doesn't work. The first reason why this is not optimal. Another reason is this depth condition, together with this X vanishing, doesn't hold for what is called an ideal module. So an example of this would be what is called, an example of an ideal module would be what is called the Jacobian module of a normal complete intersection. So it's some object that is very well studied in algebraic geometry, but not really quite understood. It's important, but we don't understand it really well. And more generally, that's some notion called ideal modules. So these are modules that in many respects are, the algebraic properties are really close to ideals. So this is not satisfied in that case. I have a result that is kind of in a similar fashion that works precisely for ideal modules. And again, it recovers the result of Johnson and Ulrich, but it needs a different proof. So it's kind of like slightly different assumptions, but there is no X condition there. It's like a different argument. Oh, by the way, I forgot to mention that for biggest possible reduction number, so when we pick K equal L minus E, this result here for Cohen-Macaulay was proved previously by Ken and Lin, but she only has that bigger values of K. But then again, it's there is another part where it's tricky. Here I'm assuming the modules will be orientable, and my main hypothesis here is what G is equal to 2. One big issue with working with generic Pourbachet ideals is the generic Pourbachet ideal, when it exists, as either height 1 or 2, if you want something that is height bigger than 3, or at least 3, the only way this can happen is that the module started with is a direct sum of an ideal plus a free modules of rank 1 less. So really, with this technique, it's almost impossible to recover any result of an ideal that is of height bigger than 2. Like, I have applications for this using this Cohen-Macaulay result. for modules of projective dimension 1, that will be the analog of perfect ideals of I2. If you work with these algebras, you want to know also perfect ideals of I3. There is no way you can tackle those like module versions of those results, because if you do even the direct sum of two ideals that are perfect of I3, I have no idea what the Riesz algebra of that direct sum of two ideals that are perfect Gorenstein of I3 is. No clue. So that's how technical this becomes. So one hope is that maybe in the case of multi-Riesz ring, so like when you have direct sum of ideals, maybe you can get around this generic Roubachier ideals. And I mean, there are some ad hoc arguments that work in the multi-Riesz case, but I don't think there is much done where you combine the multi-Riesz case with residual intersections. There are some results that use different methods, but not residual intersections.
Thanks.
I wanted to ask you about the core, because I know there are some results on the core. Is like the problem because there are like different notions of integral closure for modules like the Riesz or the Eisenbud, Haneke-Ulrich, or the liftable integral closure? I mean, is that there might be different or?
Okay, part of the problem is that the part on the integral closure could be tricky, but in this specific case, so for this result here that I was interested in, this specific result here, it's a condition on the core that uses these residual intersection properties. So really the work I'm referring with here is the work by Corso-Pollini and Ulrich, where they study the structure of the core for ideals with good residual intersection properties. The problem is that in general, this core that is intersection of all minimal reductions is an infinite intersection of ideals. So it's very hard to calculate. What they show is that under suitable assumptions on the residual intersection of the ideal, the core is a finite intersection. Yeah. And when the reduction number is bounded, they actually use this result of Johnson and Ulrich on the Cohen-Macaulayness of the Riesz algebra to prove a formula for the core. So that's what's missing in this case. Like there is a paper by Corso-Pollini and Ulrich from 2003 for modules of projective dimension 1. They calculate the core. And in that case, what they used is that they knew exactly how to characterize the Cohen-Macaulay property of the Riesz algebra, because for modules of projective dimension 1, that was done in the paper of Simic, Ulrich, and Vasconcelos. So really what was missing was this theorem. And when I discovered this, I just quickly emailed Luis and said, let's do this. And I was really happy about it because, so long story short, as I said, the case with biggest reduction number was done by Lynn. She published this recently, like I think 2016 is when the paper came out on arXiv. I don't know when it got published, some time later. But she had started working on that back then when she was a PhD student, which is pretty much at the same time when Louisa was a PhD student and Zhu Yun was a postdoc at Purdue. So what was happening back then in 2006, 2007 was that Lynn was trying to prove the Cohen-Macaulayness of Riesz algebras, and Louise and Zhu Yun were trying to apply that to the core. But then they got stuck because Lynn couldn't figure out what the trick was, and they got stuck because they needed to know when the Riesz algebra was Cohen-Macaulay. And that's where everything got forgotten until both Lynn and I got back to work on this. And so hopefully now we have the tools to finish this. That's the project. But it was a really interesting family story here. But
well, I was just curious if maybe you considered, you know, different types. I mean, just because there are sort of 3 different versions that I know of integral closure for modules. I mean, maybe one of them would work better.
I haven't thought about it.
I mean, I know that they're like Neil and Barrett have this liftable integral closure that maybe that would be easier to work with. I don't know. I just,
That's a comment. I mean, another possible thing that might have made things easier in the meantime is that recently there are some students of Woolridge that are graduating this year, Lindsay Hill and Rachel Lynn, that are working on integral closure of modules. And they generalize a result by Hong and Ulrich, where Hong and Ulrich was doing a construction involving generic Bourbaki ideals. They're doing for the general Bourbaki ideal. So you don't extend the ring, you kill general elements. So that gives a different way of thinking of integral closure of modules. So I'm thinking that could be a possible thing. Like in the paper for modules of projective dimension 1, they actually construct what is the general Bourbaki ideal. So like a similar construction, but instead of doing a generic extension, you kill general elements. And so we're still trying to figure out whether we should be using generic or general. We're also trying to figure out whether we can skip this generic and general, like trying to figure out if we can actually cook up residual intersection for modules, but that's kind of, you know, we try to think that ideals are modules of rank 1, but then at some point you have this ring structure that comes in and you figure out that when you think of them just as modules of rank 1, you're missing out. So it's not that easy.
thanks.
Cool. Let's thank Alessandra again.
Thank you, everyone.